All right.
I just know that if it was just, I think I can do a comparison test because I know if it was cosine pi n over 2, that would be like an alternating series.
Good. So all of that numerator part makes it alternate. So all of this right here can be just forgotten about when we do AST.
Even the n plus 1?
Yeah, all of it's,
Like
it's in the parentheses. It's the argument of cosine. So what you do is you drop the alternating portion, and what's the first step we have to do for that?
Take the limit as n goes to infinity of a of n, which is just 1 over n squared plus 4.
Okay,
and if it equals 0, which it does, you go on to step 2.
Okay, what if it didn't equal 0? What would you do?
Then it would diverge by divergence step.
Got it. Look at you. All right, so then what's the next condition?
You should see if it's a decreasing a of n. So you can take the derivative, or you could do that too.
Okay, we can do derivative if you want. That's up to you. Okay. You have the power to determine that. I will recommend, though, if you do have numerical values over variables, the proof is pretty easy, but let's try the derivative. How do I derive that?
Okay. That's to the negative 1 power, to the power of negative 1. And then you can just leave if it's negative, and then parentheses n squared plus 4, the power of negative 2 times 2n. And since it has a negative already, that's like less than 0.
Okay, so
that's
the domain,
positive.
Yeah, this is always greater than 0.
Mm-hmm.
And the domain of this is the natural number, so negative 2 times a positive number is going to be less than 0.
Mm-hmm. And what was the other way that you were doing it? Or
so this would give you less than 0 overall. The other way would be just to compare these two.
mm-hmm.
Which one's bigger?
The one on the right. So it would be just proving that. Okay.
And then when you take the reciprocal of both sides, change the direction of your inequality. And this tells you that the original term is bigger than the n plus 1 term. So the original is bigger than the next. In other words, what we're trying to prove. Either way works. All right, so we've proven AST, but we're not done. So now what we have to do is what? We have to look at it with
how a of n, if it diverges or converges by another test.
So what test do we use?
We could do comparison test.
Okay.
We could do limit, I think. Because I always have to write it out first to make sure if I can use direct comparison because we have to check the inequality.
Uh-huh.
So that's why I'm not always sure if I can use direct comparison.
Well, I think it might work in this case, right? Because n squared plus 4 is bigger than n squared. So when you flip it, you understand what I'm saying? So what would your b sub n?
I'm writing it out.
B sub n would equal?
B sub n, 1 over n squared.
Okay, so that's a convergent, just like a 4.
And that's bigger than the original, and if the bigger one converges, the smaller one converges.
Which is what we want.
Direct comparison. Okay. Yeah, I always just have to write it out to make sure. So that means the original theory converges. Wait, I think it converges absolutely.
Right. So now that I got that down, what's your final conclusion?
That the original theory converges absolutely.
Very good. What would have happened if it diverged at the end?
It converges conditionally.
Good. All right. I got 3 minutes before Eric's going to walk in that door yelling at me.
Okay.
That is if it shows up. But it seems like you know what you're doing, right?
Yeah, I hope.
You just got to keep practicing.
Refresh. Yeah.